Good afternoon, everyone. Hello, good afternoon. Are we there? Hello. Hello, good afternoon, everyone.
Good afternoon.
Am I audible enough?
Yes, you are.
Okay, thank you very much. I see there are only about 7 people who have joined in the meeting. How big is the class?
I'm not pretty sure. I think should be 40 something or 50 something.
Oh, okay. Anyway, we're going to start the session. Others, I think, they will join as we proceed. So just to start with, my name is Chawezi Miti. I'll take you through this course, um, through this course, and basically this course has to do with water conveyance. That's the movement of basically the movement of water. In this case, on farmlands, since we're dealing with agronomy. So I'm a soil physicist by speciality, and basically this course this course has to do with a lot of uh, physics. So we have to reorient ourselves with some basic physics. Yeah. So one thing, always remind me when we start a class so that I should record the session so that I should post it afterwards for those who miss and for those who would want to clarify on certain things. Then also make sure that your mics are muted just to avoid disturbance and some feedback. Then this Zoom session will only last for 40 minutes. So when it cuts, just use the link again to rejoin so that we complete the hour that we are allocated. Yes. So we are going to go through the course. Let me just share my screen. Okay, are we able to see the screen? Are we able to see the PowerPoint presentation?
No, we are
No.
not. No.
Okay, what's on the screen?
There's nothing.
Are we able to see it now?
Okay, we can now see the screen.
The host is around. Maybe there is something he's doing.
Your mic is off, sir. Your mic is off.
Yeah, sorry. I keep having problems because it keeps on reconnecting. It keeps on reconnecting me like the internet, so it's disturbing the flow of the session. Okay, are we able to see the screen? Okay. Okay, so as I was saying, we're going to have 4 lectures. The first one has to do with basic fluid hydraulics. Then the next one will be about water flow in pipe. The third will be water flow in open drainages. And the last one, it will talk about the drainage of agricultural lands. So we go into our first, the first one, which is talking about, which is going to concentrate on basic fluid hydraulics. So like I said, this course has to do with water movement. So in dealing with water movement, we'll look at a lot of physical properties of movement of water. So we know that for water to move from one point to another, it is governed by several water physical properties. If you have any question, you can just interrupt me, and then you ask a question as I deliver. Yeah. Okay. So we know and we have seen that in most cases, for example, here in Zambia, most of the water that we use for agricultural purposes is from the rains. But there are certain circumstances where you would want to use water maybe from rivers or from other reservoirs. So for you to use that water, you need to move it from where it is in a reservoir to your farmland to use for irrigation and other purposes that you might want on the farm. So which brings us to the core of this course, which is the conveyance of water. So the conveyance of water, which is basically the movement of water from where it is to the point where it is being needed. And like I said, all this is governed by physics, the physics of the water. For it to move from one place to another, it obeys the laws of physics. So for us to fully appreciate this course, we would have to go back a little bit and dwell on some few principles of physics, which will help us fully understand what we are talking about in this course. So on completion of this lecture or this chapter, which is basically chapter 1 in your module, at the end of it, you should be able to understand the different principles of physics which govern water flow and identify these, out of these principles, which ones affect water movement. And in the end, you have to relate it now to, how it applies, how actually that physical property will affect the design of a conveyance system that you'd want to put up on your farm or on your small holding or anything. So basically, if you're able to do these 3 things, then I'll be happy with that. Okay. Unless there are questions before we start looking at these properties. Okay. Okay. So basically, this branch of science where we are looking at the flow of water, the conveyance of water, is basically what is known as hydraulics. So it's just a branch of physics which studies the mechanical properties of water and other liquids which are in motion. So you would realize when you go into literature, it will be divided into two. There will be what we call hydrodynamics, and there will be what we call hydrostatics. So when we're dealing with hydrodynamics, we are looking at the properties of water or the characteristics of water which is in motion. So we look at the speed of water, we are looking at how the energy is changing and things like that. Then when we are looking at hydrostatics, it's where you have water which is not moving, it's just static. For example, water in reservoirs, water in ponds, water in tanks. So you look at the properties of water that is standing and not in movement. And some of these properties that we'll look at is some of them include the volume. We are looking at volume because obviously we know that at some point you would have to know how much water you want to deliver to your farm, how much water is required to be used at a particular time. So the concept of volume becomes very, very important. Then the other property is the velocity, because water is moving from a certain point to another. So you'd want to regulate the speed at which it's being transferred to your farm. You know, okay, how much time am I going to be required to irrigate? So that is in relation to the velocity, how much time it's spending from the point of where it's coming from to your farm. This is also related to the acceleration, how much acceleration it's taking, and also the force, because for water to move, you need to apply a certain force. So we need to know concepts of force. Then friction as well, we'll look at it in the later chapters. So this friction will be just the energy losses as water is being delivered through pipes. It will also come through when we are looking at open drainages and pipes as well. But for now, we just look at it in brief, just as friction. Okay, so we can look at these properties one by one. I'm sure some of them you know them already, and you've used them in various aspects. Those who are dealing with water and other areas, I'm sure you've seen some of these parameters. So the first one that we'll look at is the volume. So the volume is, like I said, will determine how much water you need. So it's important you know what volume is and how it can be calculated. So from our basic physics, we know that the volume will be equal to the area of where your water is, be it a pipe, be it a tank, and then multiplied by the height. So that gives you the entire space where that water is occupied. So area times height will give you the volume of a vessel. But it's not all vessels which are of the same shape. So if you're looking at something which is rectangular, so something which is rectangular, for you to calculate the area, it will just be the length multiplied by the width of that container or tank or anything. But if that vessel is not rectangular, you need to improvise now and check other methods of calculating the area. So if it's circular, if your base is circular, for example, for you to calculate the area, you need to multiply the radius of that vessel, multiply by pi, then you get your area. So basically, volume will be the amount of space occupied by occupied by water in this case. Then the second principle, the second property that we'll look at is the density. So the density is basically just the mass per unit volume of a substance. So in this case, the mass per unit substance of water in this case. And for water, for pure water, the density is usually 1 gram per centimeter cubic. So density will come in more critical in this course because in most of the time, we are not dealing with the mass of water, but for us to relate it to the volume, we'll be using the density. So basically the density is more important in this course because we do not use mass when we're calculating any physical parameters for water, because we know that for every mass, for every gram of water, it occupies a space of 1 cubic centimeter. So we won't use mass, but we just use density and volume. The other parameter is the specific weight as well, because we know that the density of water is constant, that's pure water. So in most cases, we'll just be giving the specific weight, which is the density multiplied by the gravity. The gravity as well, we know that it's constant. So when you multiply density and gravity, it will give you a specific weight of water. So we'll see as we go when we use this parameter, but just bear in mind that the specific weight is the density multiplied by the gravity of water. The gravity, the gravity of the earth pulling on the water or any substance. Then the specific gravity, this one won't use it much in this course because it's usually used when we want to relate other fluids to water. So it's just a ratio of the density of a fluid, maybe petrol or any other fluid, to that of water. So if you are doing computations, you might first start by calculating it as if you're calculating for water, and then now change it to another liquid which you're studying. For example, if it's petrol, using this ratio of specific gravity. Then we can also look at the velocity and acceleration. So when we're talking of velocity, it's just basically the rate, the change of distance with time. So how fast is the water moving in your pipe or in your drainage or in your open channel? How fast is it moving? So this will determine how much time we are going to let your water flow, either in the pipe or in the open drainage. So if you know that, okay, I'm supposed to supply this amount of water, 10 cubic meters of water, you need to know, okay, in how much time am I going to deliver this water? So that's why the concept of velocity comes in very handy. It's similar to acceleration. They are interrelated because acceleration now is the rate of change of velocity with time. So as the velocity is changing, whether it's if it's increasing, it means that you will need less less time to deliver your water because it's coming into your field very fast. Then now, because we say that for water to move in a pipe or for water to move in a open drainage, you would need to apply a force to it. In short, you need to push it. So we need to understand what force is and how it is related to the water movement. How much force do I need to apply to move water from point A to point B? And force, if we are looking at force, we can look at it with three laws. I'm sure you've seen these three laws. Those who have done physics, I'm sure most of you have done physics either in your secondary school or at tertiary level. So if we talk of force, we can define it or relate it using three laws of physics. So the first law will state that if a body if a body is seated, for example, on a table, and if no force is applied to it, if you don't push it, then that body will remain as it is. If there's nothing which is pushing it, it will remain as it is. So if, for example, if you take your phone, you put it on your table, it will remain there until you start to apply a force to it, until you start to push it. So that's what the first law of force says. Then the second law now further adds on to it to say, if that body has to move, you need to apply a force which is equivalent to the mass of that object multiplied by the acceleration, meaning that multiplied by the speed of which you want it to move. If you want it to move slowly, it means that you apply a lesser force than when you want it to move fast. So because the mass of that object will remain constant, so it means that the acceleration is what now would determine the force that is required to push that object. So in this case as well, when we are relating to water, if you have a certain volume of water, you need to know how much force to apply for you to move it from where it is to where you want it to go. Then the third law says that if an object is moving at a constant speed or a constant velocity, it will continue to move until a certain force that is equal to its force opposes it. That's when it will stop moving. So this will have an implication when we start talking about the frictional forces in pipes and in open drainages. So these are the three laws of Newton's three laws on force, which we need to know because they will be applied as we start looking at the movement of water in the pipes, in the drainage, and in open channels. So just an illustration of the concept of force. We can see the block on top, which has it has a mass of 5, and the acceleration is 3 meters per second squared. So if you want to know how much force is required to move that object, you need to multiply the mass, which is 5 kgs, multiplied by the acceleration of, that is the speed which you want it to move. So in this case, if we multiply 3 by 5, it will give us 15. But if I want to move this object at a higher speed, then I would need to increase the acceleration of this object. So in that case, I will need to apply a much higher force. So in this case, if I want to move it at a higher speed, I apply a force of 30 newtons, which is basically the product of the mass multiplied by the acceleration. So that's just a basic basic physics. Any questions so far?
Clear, no questions.
Okay.
Sir, sorry,
Yes,
just repeat a bit on the density of the pure water on the units. You said 1 gram per meter cubed or centimeter cubed?
centimeter cubed.
Centimeter.
Yes. So if you want
Thank
to,
you.
yes, you can also convert it to 1,000 kgs per meter cubic if you want to work in those other units. But it's 1 gram a centimeter cubic. Okay. So we can move on to another concept. We mentioned it. So in the third law of physics of Newton's law, it says that something which is in motion will continue to move until a force that is opposite it has become equal to it, so that object now will stop. So every object that is moving in nature always has an opposing force. Otherwise, everything in nature would have been constantly moving. So the force that opposes movement of an object is what we call friction. So friction is a force that objects the movement of an object. So for every moving object, there's always a force that is opposing it. And this friction we can divide it into two. It has two components. So there's the static and the kinetic friction. So when we say the static friction, it means that, for example, like I'll use the example for the phone as well. If I put a phone on a table, it's not moving if I just put it here. It's not moving because already there's what we call static friction, which is opposing its movement. Then if I start to slide this phone on the table, because of the contact between the phone and the table, because of that contact, this contact will be opposing the movement of this phone on the table. So if your table is smooth, the opposing force will be less. If it's rough, the opposing force will be high. So that's the kinetic friction, the friction which opposes the movement, the sliding. Then the static friction is the friction which comes about because of the resistance of an object to move, to start the actual movement. So there are two things there. There's the friction which resists the phone from starting to slide. Then when it starts to slide, there's the force which opposes it from as it slides on the table. I hope that one is clear.
May you repeat on that point again?
Okay. if I put a phone on the table or a brick or any object, okay, it will not be moving. It will be static because there's a static friction between the table and the phone itself. Okay, so this static friction is equivalent to the amount of force that you would need to apply to it for it to start to move. Okay, so those who have any object around, maybe we can just try to do a small illustration. You put it on a table or any surface that you have there. Then just hold it, maybe hold it behind, and then you start to apply a force, but just start gradually until it starts to move. Okay, so before that thing started to move, you were applying a force, but it wasn't moving. Okay, so that force which was opposing it to move is what we call the static friction. Number one. Then now, as this thing is, as that object is moving, if it's moving slowly, it's moving slowly because now on your surface there, it's being objected by the surface to move. But as you increase the force that you apply to it, it will start moving fast. So the difference between it's moving fast and it's moving slow was the friction that is there between the table and the phone. So those are the two components of friction. So when you add those two together, they bring about what we just call now the actual friction. But when we come to talk of the movement of water, the actual movement of water, I think we're going to illustrate more on these two parameters. Okay, then the other parameter that we can look at is pressure. We know that when we open our taps at home or any other place, we usually say, no, there's low pressure, there's high pressure, and things like that. So what we mean basically there, we're just talking about the force. The force, how forceful the water is coming out. So we need to know that concept of force for us to relate it to the movement, the delivery of water to our fields, because obviously we would need maybe water to be flowing at a higher pressure to our field for us to complete our tasks in a shorter period of time. If we have lower pressure, it means that the water reaching our farm or our reservoirs would take a lot of time for us to fill in our reservoirs and or maybe irrigate if we have a lower pressure. So basically, pressure by definition is the force that is exerted per unit area of a container or whatever vessel that the water is being kept. So when we talk of water, when we talk of water pressure, it has a different approach than when we're talking about any other object in terms of pressure, because when we're talking of water, there's what we call the pressure head. So the pressure head is basically just the height of water above a certain a certain surface. So if you have a tank, for example, as it is in this slide, we can see that there's a cylindrical tank here. So the force or the pressure that this water is going to have in this tank will be equivalent to the force that is being applied at the base of this vessel. So the amount of water in the tank, because it's leaning on this the base of this tank, so it's creating a pressure. So when we're talking of pressure, if we are asked how much pressure is there in this system, it's just basically how much weight of water is being forced on the surface of that tank. So the weight of water is what constitutes the force of that system. So if you can see from this illustration, the pressure, which is P, is equals to F over A. So it's force over area. Okay. Now, like I said, for water, the pressure is measured in what we call head. And head is just basically the height of water above the surface of a tank or of any vessel that is holding the water. So if you look to the right of your PowerPoint there, so the first line, we see that it's saying that pressure is equals to force over area. Okay. Now we can further simplify this one and say, okay, we know that force from the previous slides, we said that force is equals to mass times acceleration. Okay. Now, the mass of a substance, you remember when I talked of density, I said we will not be using mass, but we'll use density because it's more applicable than the mass. So if from that formula for density, we know that the mass of a substance is equal to the density times the volume. So we have substituted the mass with the density multiplied by the volume. So you see in the that second line of the formula for pressure, it's written as density times volume times g, which is the acceleration due to gravity. So this the whole lot of this now makes the force. Okay, so density times volume times acceleration due to gravity is the force. But we also know that the volume of a vessel is equals to the area times the height. So where we have volume, we have replaced it with AH, which is the area multiplied by the height. And once we do that, we see that we have area in the denominator, and it's also appearing there on top. So we can cancel these two, the area down and the area up. Then in that case, now we're going to have pressure is equals to density times acceleration due to gravity times the height. But we know that the density of water, like I mentioned, is a constant. It's 1. And the gravity as well, it's a constant, which is 10 meters per second squared. So those ones are constant. So for pressure to change, the only thing that is affecting it is the height of the water. So as the height of the water in the tank increases, so does the pressure increase. If it reduces, then it also reduces the pressure. So when we're talking of water pressure, we're just talking about the height of water in the tank. Is that one okay? Or I should repeat?
I think you can repeat
It's okay.
just a bit. On my part, I think you can just repeat on the constant part.
Okay, so I'll just try and go through the whole thing. So if we have a tank and there's water, just as it is depicted in the diagram there, the pressure, the pressure will be equivalent to the weight of that water on the surface of the tank. So we know that pressure is equal to force over area. So the force that is being exerted on the base of the tank. But when we talk of force, we know that force is the mass times the acceleration. And from the formula for density, we said that density is equal to mass over volume. So for us to find mass, it's just basically density times volume, which we have now replaced in the second line. So this rho, which looks like a P, multiplied by V, that becomes our mass. Then the G, which is the acceleration due to gravity. When we multiply those three, it gives us force. So that's force over area. But also we know that volume is the product of area and the height. So in the third line there, we've included area and height to replace the V. But when we do that now, we see that there is area in the denominator, and we also have area here on top where we changed it from volume. So we can cancel those two such that the area now has no effect. And in the end, the pressure calculation would just be the product of the density, the acceleration due to gravity, and the height of the water, which is h. But we know that the density of water is 1. It will always be 1 if it's pure water. So in this case, the density is a constant and the acceleration due to gravity is a constant. So the only thing which is affecting the pressure is the height, which is h, such that when we're dealing with water pressure, you would just say the pressure of water is 1 meter, or the pressure of water is 2 meters, based on the height of the water in that tank. So the pressure for water will be given in meters, in units of height, and not in, yes, you can convert it to pascals and other units, but for water, basically, when we say what is the pressure of water, we just say 3 meters. What's the pressure of water? 2 meters, because it's just basically the height of water in a tank. Yeah, so that's the concept. Okay, so I'll move to the next concept, which is discharge. So like I've always been saying, in reality, what we want is to know the volume of water. How much water am I going to deliver to my field? Or how much water am I going to deliver to my reservoir or anything on the farm? So basically, when we're talking of the rate at which you're delivering water to your farm, we are basically talking of the discharge. So if I say, what is the discharge of your system? You're going to give me a unit to say, okay, I'm able to deliver 1,000 or 1,000,000 cubic meters of water in an hour to my farm. So when you know that, okay, I want to irrigate with a certain amount of water. So for example, if in the next I don't know if it's next semester or next academic year, there will be a course on irrigation. So when you're dealing with irrigation, you want to know how much water you want to supply to your farm. How much water is required for you to irrigate the whole area. So if you know the discharge of your system to know, okay, I'm able to deliver this amount of water to my farm, then you can be able to calculate how much time you need to irrigate. So the concept of discharge comes in handy, as it is the volume of water being delivered or passing through a certain point in a unit time, be it in seconds, be it in hours, or any other unit that you would want to use. So discharge is basically the volume per unit time. Okay, so but we know, if we take a look at this diagram on the right, it's showing water passing through a pipe. So if we look at the formula for discharge just below that pipe, discharge, that's the one with the Q there, we see that it's equal to the volume of water divided by the time. So it's the volume per unit time. But we know that the volume is equals to the area of the vessel multiplied by the height, which in this case, which is they put it as D, because they are looking at how much, they are looking at the distance in which water is traveling. So the volume will be equal to the area times the distance, or the height, if you want, over time. But if you take that D, if you just take that D over T, this describes the velocity. So D over T is the velocity, such that in the end, the discharge will be equal to the area of your vessel multiplied by the velocity at which the water is moving. So if you know the diameter of your pipe, meaning that you know the area, and you know the velocity, the speed at which the water is moving, then when you multiply those two, you get your discharge. It will give you the volume of water that is being delivered to your farm in a unit time. So basically, when we talk of discharge, we can calculate it as area. Just multiply the area multiplied by the velocity. Then you get your discharge, which is the volume of water being delivered to your farm or wherever. Then remember, we said that for water to move, it needs to be pushed. like the example gave for the phone, there's need for some energy to be applied to it. So for every water movement, there's always energy that is applied to it for it to move. So that energy will produce a force, and that force now would drive the water. So there are two things. There's what we call potential energy and kinetic energy. So the potential energy is just the energy that is possessed by an object due to the height. So for example, if you take any object, if you put it on the floor, it will remain on the floor because now it doesn't have any energy to move. But if I lift it up and then I let go of it, it will move because now it has gained some energy because of me lifting it up. So as it goes up, it needs to come back because it's being pulled by the force of gravity. So that ability to move from the point, the height where you have pushed it, to come down is what we call the potential energy. And it's basically determined by the mass of that object and the height to which you raise it. So if you raise something very heavy above, it will come down very fast compared to when you put something which is very light. So the higher the mass, the higher the energy. And the higher the height, the higher the energy. So this concept is important because water moves usually from a high position to a lower position. So for example, if you have a slope and water is on top of the slope, because on top of the slope there, it's on a higher elevation, it has higher energy. So it will start to move to the point where it will move down slope because of that energy that it has due to height, which is the potential energy. Then as it starts to move, because energy cannot be lost and cannot be gained. So potential energy will start to be converted to kinetic energy, which is the energy due to movement. So the kinetic energy now will start to come in as the water starts to move or that object starts to move. So if an object has a certain potential energy, it will start to convert that energy to kinetic energy as it is moving until again it goes to rest position where it will possess potential energy. So the kinetic energy is basically just associated with the movement, and it's given by that formula here, which is just below the slide, which is half the mass times the velocity squared. So the kinetic energy is the energy associated with water movement. So these two forms now will relate now to how much energy do I need to push water from a certain point to another. If it's on a slope, water will just move on its own because it has a potential energy. But if, for example, you want to move water from downslope, upslope, how much energy do you need to push it up there? So for example, if your farm is upland and you're getting water from a river which is downslope, you need to apply a certain energy to it for you to move it upslope and onto your farm. So this energy, you need to calculate it to know it so that you know how much electricity, for example, you should buy for you to be able to generate that power to take it to to where you want it to, where you want the water to go. So which is what is in this last slide. So power basically will be power, for example, the power that we buy for Zesco. You need to know how many kilowatts should I use to generate a certain amount of energy to be able to drive this water to my farm. So basically, if you know the amount of energy that you need, then you also know the amount of time that you need to irrigate your farm. If you take the energy and then divide it by the time, you get your power, you get your unit of power. So when you get that unit of power, you know that, okay, I need this amount of units. For example, if you get Zesco units or electricity units, you know that I need this amount of units for me to irrigate my farm. So the concept of power now comes in handy as well. If now you want to know how much money you're going to spend on your irrigation, because you know that you use how many kilowatts of power for you to irrigate your farm, or for you to move your water from the river to your reservoir. So these are the basic concepts that I wanted us to go through before now we go into the actual flow of water in pipes and in open drains. So I think for today we're going to leave it here. Then tomorrow we'll continue from there. So if there are any questions, maybe you can raise them so that I can answer them in readiness for tomorrow's session. But also, I think the session is going to cut anytime soon. So when it cuts, you can just rejoin using the same link that I sent. So if there are questions, you can ask. Are there any questions?
For me, I don't have any question.
Okay, that's good. Anyone who wants to ask a question, you can just unmute your mic and then you ask. Okay, so yeah, so one other thing that I'll do, I'll try to generate some examples of these concepts that we have been doing. Then maybe I'll be posting them on I don't know whether WhatsApp or on the platform, whichever is okay, just to appreciate these concepts that we've been going through. Maybe I'll give a problem, then with a solution on how to go about it, so that we're able to appreciate some of these concepts.
Oh, yeah, interesting concepts, especially on pressure.
Yeah.
I think it was interesting to learn that pressure is equal to 10 meters on a right or not.
Yeah. Yeah. So for water, pressure would be in meters. So you say, okay, I have a pressure of 5 meters, a pressure of 10 meters, then someone will understand that, okay, it's this. It's just basically the height.
Don't forget to send the recording after the lesson is done.
Okay, no problem. Okay, so should I send it via WhatsApp or I send it on the platform? Which one is okay? Or I'll send on both.
I don't know if you can manage depending on the size, but other lectures like Dr. Chalwe has been sending it via YouTube.
Oh, okay, okay. Yeah, I think that's a better option.
Yes,
Okay.
then sending them to our email addresses, or you can send it to the class rep, then he can send it to all of us.
Okay. Okay, no problem. I'll do that. Yeah. Then okay, I think if there's no other question, I think we can meet tomorrow at the same time.
All right, thank you, Doc, for today's
All right.
lecture.
Thank you.
Okay. Okay, thank you. Have a good day.
Tupae mistari.
Alik, congratulations, zero wa meeting ako Mike.